Welcome to this session. So the goal of this session is actually to give the opportunity to the project we just selected in the last call to make the case for their project and really introduce themselves to the community. And it's a good way also to start discussing with the other project which might have some common goals. And also, if you are interested by their research, so please go and visit their posters. So there will be a poster session right after this session, and it will be just before the exhibition. So since after this you will all rush for coffee, so please stop by the poster session, which is just when you go down in the same floor as the coffee, just before the exhibition room. So out of this call, we selected 16 projects, and then we have an additional as well to deal with non-technical issues, so legal, ethical issue as well, and societal issue as well. So I'm going to, so we have all the presentation in a single, gathered in a single presentation, and each of the presenter is sitting in the front row, and one by one they will come to present it. So, oops, of course, I'm here. So this was the result of this H2020 call. So the first topics we will address today is the healthcare topic, and in that topic we have selected 3 projects, one on prosthetics, one on helping care home system, and one on surgical robotics. And the first one we are going to present is the CYBERLEG, so a cybernetic lower limb cognitive ortho-prosthesis project, and this is a follow-up of an existing project. So I give the floor, to Nicolas to present it.
Yeah, good afternoon to everybody. Yeah, the objective of the CYBERLEGs project is to improve the quality of life of transfemoral amputees. In particular, those amputees that have vascular problems and that they usually do not use any prosthesis. The idea is to develop both new prostheses and new exoskeletons in a modular way that can be used in several activities of daily living and also during the rehabilitation process. We start from the results of a previous project, an FP7 project. Actually, the starting point are several advancements from the technological viewpoint in terms of series elastic actuators, novel kinematic solution for exoskeletons, and non-invasive interfaces, and some prototypes about prosthesis and exoskeletons, and proof of concept in terms of new bio-inspired solution for control strategies. This in strong, actually is as an input for a strong synergy between academia, industry, and clinics, will actually be the methodology that we will follow. And the idea is to basically validate from both economic viewpoint and clinical viewpoint the technology. Of course, we address impact from the scientific viewpoint. We want to increase the market readiness of this technology. We want to assess efficacy of the solutions and the viability of, from the economic viewpoint of the solution. And we want to get an impact in the healthcare domain, improving quality of life and giving new solutions for the treatment of vascular amputees. And of course, also beyond the amputation issues in other lower limb impairments, in particular with the exoskeletons. Of course, we expect to help young companies like one of the company in the consortium to grow up. And of course, we expect a significant impact from the economic viewpoint. Of course, what you see here is a quite optimistic view, but actually dreaming is an important ingredient in this project. And that's it.
Thank you.
Our project is Move Care. Actually, it's tackle the problem that have to face people when they get old, especially pre-frailty people who get a recovery nursery home maybe too early with respect to the possibilities. And what we see is a large number of different components that only put together and developed further can help tackling their problem. And the idea of Move Care is to provide the basic high-level functionalities for keeping the elder at home alone in a safe way. So we aim to develop monitoring, assisting the elderly in some of the typical functions, and provide the way to give them activities that promote socialization. That actually is one of the drives that delay the onset of possible cognitive and physical decline. On the technological aspect, we aim to develop indexes that evaluate the complex system that comes out from the interaction of the different components. And actually, the overview of the platform that we are going to develop is the following. We will have a domotic system to acquire information from the environment, smart objects, to acquire information of the interaction with object for physical monitoring. A virtual community will be the basis for social activity, an activity center that will promote these activities to the single elder, a robotic platform that will work as a movable, say, node to provide these activities, and we will integrate all these components through a virtual caregiver and with artificial intelligence will promote the best suitable activities, look at these activities, and derive cognitive and physical indexes of possible decline. And one of the peculiarities of this project is that we are not aiming to put anything to the elder. He will continue the life as he was doing before, and we will try to put all the intelligence distributed inside the environment. As far as the robotic platform, we have chosen already existing industrial platform, that is the GIREF platform, and we will develop it further to make it an empathic companion, looking at proximity and how the virtual caregiver can interact through the robot with the elder. And actually the impact that we are envisioning is try to transform the third age into a good period of life. Usually third age is associated to decline, but old people, we think, have a lot of richness for their experience, and we want that this experience can be distributed to the society. And again, tighten also the bonds with the parents and other caregivers that usually live in other places. On the other side, we hope we can help national service providers to better allocate resources and develop a new model of care that can take into account also technology. And from the technological point of view, besides evaluating this from the functional point of view, a structural point of view, this heterogeneous system, we are aiming to explore how to combine, have some guidelines and some determinant how to develop gamification and robotics inside the ambient-assisted living. So, thank you.
Tanya, welcome.
Hello. Good afternoon. My name is Tanya Dogramazi. I'm from Bristol Robotics Lab in the United Kingdom. So Smart Search project has been set up to investigate current limitations and opportunities to advance robot-assisted minimally invasive surgery. We have brought together 4 surgical partners, 4 user participants, 3 academic partners, and 3 companies interested in medical robotics to develop new robotic technologies for 3 surgical use cases. Minimally invasive surgery has become now an established alternative to open access conventional surgery, providing sufficient evidence that it can actually offer better outcomes for patients than conventional surgery. It is unfortunately currently limited to only a certain number of surgeries, and due to limitations in the existing robot-assisted technologies. Medical robotics market currently takes about 1/3 of the overall service robots market, and due to the increasing population will actually expand further in the years to come. Our ambition, our goal is to improve the efficiency of the current minimally invasive surgeries and also to expand applicabilities to other surgeries where the open access is still the gold standard. In order to do this, we would like to improve the current robotic abilities, to improve efficiency and accuracy of the surgery, to reduce the surgery time, and to also reduce the length of the training that the junior doctors require to attain the skills. Our proposed methodology starts with the user-centered development through short developed test cycles and keeping the clinicians at the center of the development. The three academic partners are working on new master-slave instruments to improve access and articulation, and also to improve precision in the surgery, to develop haptic feedback and improved visualization for enhanced situational awareness, and virtual reality glasses and dynamic active constraints to provide safe surgical manipulation. Of course, the impact we are hoping for is to address the surgeries that have a high incidence and high cost and currently receive little research attention as economic impact goes. For the social impact is that will be realized through designing more effective but also more affordable and widely used technologies for better patient outcomes. And we believe that academia and industry will more widely benefit from improvements on various aspects of teleoperated robotic techniques. That's it.
Thank you. Now we move to a different sector, which is manufacturing. Oops, sorry. And there we have 3 projects to start with, and the first one, so one is more like a kind of exoskeleton. We will hear more about that. Another one is really more research-oriented and trying to understand the effect of your action, and then it will be demonstrated in a manipulation task, in a disassembly task. And another one is to use a mobile platform, a mobile manipulation platform in production line. So the first one is An.Dy, and Francesco, the floor is yours.
Thank you. So the idea of this project is represented with a trivial idea. So we are used to robots in the cage where no humans, with no human around. And nowadays there are a few applications where you can see robots coexisting with humans. So I had these 3 sort of dreams in mind. One is concerns Joanna, the second one concerns James, and the third one is John. Just 3 names with J. Not really a reason for that. But Joanna is basically working in a factory. And the idea that she's working with a normal sort of suit, but it's a new suit. It's different from what she was wearing some time ago, because she has within the suit a number of sensors that allow the collaborative robots in her company to know exactly what Joanna is doing. Not only the position she is assuming, but also the forces she is exchanging with the workpiece they are working together. And the idea is that thanks to this information, the cobots in the company can anticipate the ergonomic effort of a specific action and adapt their control action in such a way that the ergonomic stress is reduced. A similar idea with exoskeletons in scenario 2, which involves James, is the idea that the suit now is not only the information that is taken from the human, but also this information is given to an exoskeleton. And the exoskeleton can understand what the human is doing and therefore adapt the control action to the specific movement that the person is performing. The third scenario, which is the most advanced one, and indeed is a sort of a dreamlike scenario, is about assistance of elderly people at home. So the idea in this case was to imagine a person that has start feeling that his muscles are losing strength, and therefore is dreaming by reading a book from Asimov, is like dreaming of a humanoid robot that sooner or later will help him in doing things that nowadays he's afraid of doing because he's feeling that his muscles are no longer as strong as they were. So all these scenarios have something in common, and the commonality is physical human-robot interaction. And the idea of this project is to start thinking that what is so specific about physical human-robot interaction. And for me, it's prediction. So the ability to anticipate what the other person is doing. This, I think, is crucial in any physical human-robot interaction, and there's not enough investigation in this. But for doing prediction, we need models. And in the proposal, I was writing that to anticipate the movement of a planet, you need a model of the solar system. You need a Newton's law. You need to know how things evolve in time. And to build models, you need observations. You need to have the location of the planets on the sky. And last but not least, to obtain the position of the planets, you need new technologies. So you need, in this case, the telescope to look at the planets, how they move in the sky horizon. So that's reversing this idea. We need to start with technologies. And the technology we are building is in collaboration with Xsense and with my institution, the Italian Institute of Technology, a wearable suit that allows to measure position and forces that person are applying to the environment, and also the musculoskeletal stress on their body. And once we have the technology, we can have a data set, so we can have the observations, and this will be the second outcome of the project. So a set of observations that will describe a certain specific set of actions. And then we go to models. Oops, once more. We go to models, so we will build different models. We will start with biomechanical models, but we will also consider ergonomic models, classification models, and last but not least, models that will predict the behavior of a person while doing a standard movement. And the scenarios of application of this technology is we have three different scenarios, very similar to what I was presenting at the beginning. So on one side, we have the industrial scenario, the other one, the exoskeleton, and the third one, the collaboration with humanoids. And that's it. I think
Perfect.
There's no time for questions.
Thanks.
So I'm interested in robots that understand their environment such that they can interact with it meaningfully. And I want the robots to acquire this understanding by learning from experience. And so scenarios that I might be interested in is household robotics, right? You have a robot in your household that helps you clean up your kitchen and so on. And in order to do that, it needs to understand that cups cannot be turned over when they're full, but they can be when they're empty, and all this kind of things that infants learn as they grow up. But it turns out that there's no funding in Horizon 2020 for household robots. So then one of our partners came up with an ingenious idea of doing recycling instead. So this is not manufacturing, this is the opposite, this is about disassembly. And you need this kind of understanding in disassembly because you don't have design documents, there are no procedures for taking things apart as opposed to for putting things together. So here's our scenario. This project is a spiritual descendant of our experience project that you may have heard of, where the objective was to learn structure that you can exploit to make future learning easier. And we had some success in learning things and learning more things on top of those things already learned, but we didn't really learn structure in the physical sense of interacting parts. And this is the gap that Imagine is intended to close. So the idea is that the robot basically has two parts to his brain. One is a statistics-based machine learning type generative model that says something like, if I pull here, then this will fall down, or if I turn this screw, then it'll come out and it'll release this part. Much like human intuition works. But then intuition is not all. Humans also apply structural reasoning, and we want the robot to apply structural reasoning as well. So in addition to the machine learning type generative model, it will also contain a full-blown physics simulator in its brain. And then the robot will be able to reason about structured finds in the world. And Imagine is about putting these two things together, guessing the structural parameters, the physical parameters of the world to allow the physics simulator to make reliable predictions. And then, as I said, the application domain is recycling, in particular of electromechanical devices, and this is a very nice application domain because there's a lot of need for automation, because a lot of recyclables these days are just shipped to Africa and dumped and cause great health hazards instead of being dismantled because it's just too expensive. So this gives you a glimpse of what might happen, how these things collaborate. So let's focus on this high saturation region on the bottom left. We work with action descriptors that are building blocks for a planner to use. That's not shown in this picture. So it chooses an action, it's fed to the execution engine, the physical robot, which produces a new situation in the world. But at the same time, there's the association engine, which was the left half of the brain, the machine learning-based system that produces an estimate of the outcome. And there's also the physics simulator that also produces an estimate of the outcome. And the sensing system sees what the actual outcome is. So now we have two different predictions and an actual outcome. And those three will then be considered by a calibration system that makes sure that the predictions made by the two simulators are realistic. And then on the right-hand side of the picture, there's more. So for example, if the predicted outcome does not match the actual outcome, then the physics simulator can be recruited to try to guess what went wrong. And so for example, it figures out that if it changes the force applied to the lever, then it'll probably work, so it can just try again. Or if the physics simulator determines that the action was not applicable or something, then things go back to the planner. So this is a high-level view of a scenario that might happen in the collaboration of these different parts. And finally, expected impact of the Imagine project. In addition to the high-level reasoning and understanding outcomes that I just described, there will be progress in advanced functional simulation. So one of our partners is an expert in simulation, in particular of ruptures and liquids, such as those things that we need in the concept of disassembly, skill transfer, structural understanding, and of course many other, and we'll build a multifunctional gripper tailored to the assembly scenarios, and my time's up, so I will stop here.
Thank you.
Dipping a bit deeper in manufacturing. So I'm leading the manufacturing groups for robotics in Technalia, and we're coordinating the Versatile project. So in Versatile, basically, we are focusing in manufacturing tasks in the context of high mix, low volume, so lots of new products variants. We all want customized product today, so this is impacting a lot the manufacturing lines. And how can we cope with something that allows this to be most cost efficient in terms of robotics deployment? So I think that one of the objectives of today was to connect. I think one of these objectives is connected, because what you would like to do with the dismantling, when you have the plan, our objective is to be able to do it, okay? So lots of different objects to dismantle or to ensemble, and that's what we're going to work towards. So we have three pillars in Versatile. One is to be able to program much more efficiently the production tasks, okay? So based on taking information directly from the CAD to make the product plan, to make the assembly plan and all these skills combinations to be able to set up your cell quickly. Second pillar, and of course, when you know what you have to do in the context of lots of different products to Ansible with the same system, you need to perceive your environment. And here we have a big focus also on perception for operations. And the third pillar is on the concept that most of the manual tasks today, they are still manual because they are either very complex or because you need two hands. If you need to put a component to screw it on a dashboard on a car, it's much better to have two hands. So we are going to work on dual arm robots, not only dual arm manipulation, but mobile dual arm manipulation. Because in lots of the factories, you need to move from a cell to another cell, or you have your product is moving through the line. So how can we combine mobility with dual arm manipulations? So these are, let's say, the three main technological pillars that we will focus on. In terms of impact, instead of reading this slide, I will go back to the first one, where we have the consortium. So in the consortium, we are really industrial consortium. We have 3 end users, Airbus, BIC, and PSA. These are not SMEs, okay? But the goal is that when we make these technologies available with these people that are capable to push towards technologies, these technologies will be available for SMEs. So the 3 companies, they have needs in their plants that are not fulfilled today by the technology. So we are teaming up with the University of Montpellier, the LIAM labs, and LMS in Greece to develop some scientific aspects on the 3 pillars that I've mentioned. And then we are both Tecnalia, Intermodalics, Comau, and DDH, more the technology providers. DDH is a Spanish integrator. So basically what we want is a project that will mature those technologies and make sure that they are applied in use cases, and make sure also that with the help of the technology providers and integrators, we'll be able to be shipped to different clients later on. And that's how we're going to make the impact of the project. Thank you very much. I go through the slides for the next one.
Thank you. So move to a different application domain, and it will be in the civil sector, where we can also see robots helping us very much. So Carlos will explain us how his Badger project will help in the civil sector. Here it is.
Thanks, Cecile. Good evening. Badger project try to make the cities more clean and livable, and this is why the main motivation is to reduce the number of street walks, especially in the urban environment. There are about 600,000 trench in big European cities every year, and it's really create a big traffic problem, but not only a traffic problem, but also problem for the pedestrians, noise, etc. The estimated cost is about 80 million euros of this kind of problem that each European city has. This is why the goal of the project is to develop a trenchless autonomous construction robot. This robot making small tunnels, mainly for the communication, for example, internet, fiber optic, or for the gas pipes, or the small water pipes. With this autonomous robot, we can avoid to make a trench in the city, maintain the same traffic, the same clean area. The idea is to have an autonomous device that are moving among a lot of underground obstacle, using a penetrated radar and several other sensors and also gather all the data of the underground in order to construct a model and use it in the next possible excavations. The approach is a modular system. It means we add several modules. We are thinking in the diameter of 2,000, 3,000 millimeters, and we introduce several very novel technique like ultrasonic drill top system, also a 3D printing device for wall supporting, and of course all the systems are on board, and we have performed complex 3D navigation. The impact, and this is very important for us, is to introduce and create robotic technologies for civil urban underground sector, but also to introduce new applications like search and rescue, mining, mapping of the city, etc., etc. With all this technology, we think that we have a new European advanced sector. Thank you very much.
Thank you. Now moving to yet another domain, what is called commercial domain in the multi-annual roadmap and the strategic research agenda. Here we have two types of application: use of multi-drones for media production and another one in construction. So the first one is multi-drone.
Hi, my name is Peter. I'm professor at the University of Bristol, who is the coordinator of this exciting project. All of you know that we already use drones for media production. This means, and you see in your TV very nice shots. So what's the new about it? So our ambition, first of all, is to use multiple drones. And not only this, we have to use multiple drones for AV shooting in areas where there are athletes and also crowds. And this has a lot to do with safety, autonomy. So this means that we have to increase the multi-drone system. It's autonomy, decisional autonomy primarily, robustness and safety. And how we do this? First of all, with proper mission planning, and this means flight planning and also controlling cameras and so on. And this system is not really fully autonomous. It has a director and other crew members that they have to interact with the system. So essentially, we have human-in-the-loop issues that we have to address. And during multiple drone mission execution, we have a number of safety issues. For example, there are no-flight zones. We have to avoid crowd. We have to observe any aviation rules that exist at this place and time and so on. And of course, we have problems with with robustness of the multiple drone communications, because imagine the case that somebody takes control over the system and then it throws it to the ground. It's really dangerous. So we have a lot of issues that are related to autonomy, robustness, and safety. And then we have a new, exciting media world, which is drone cinematography. So how can we do it? How can we do it efficiently, and how can we provide new user experience? That's the overall idea, and that's the innovation from the media side point of view. And of course, to do this, we have to understand, first of all, what's drone cinematography. We have to quantify it, and we have to provide various tools that some of them do not exist so far. For example, if you have a bicycle in Giro d'Italia that moves at 50 or 60 kilometers an hour, how you track it, how you identify athletes, how you identify persons, crowds, that is going to help you in the decision making. So all these are important aspects that we have to deal. And In our approach, of course, in those cases, in production, you have pre-production and production. So what do we do in production, in pre-production? First of all, we have to plan the mission. This means to plan the path, the flight path and flight zones, and also how we're going to shoot and how we're going to control the cameras. And then we have the production phase. This means during the day of the Giro d'Italia race, we have to actively understand where the drones are and guide them appropriately so that they execute their mission. So in pre-production, we have to model our world semantically. For example, we have to explicitly say where are the possible emergency landing sites, and we have to plan the entire mission. Then during production, we have to control the drones. We have to control their formation as it follows the target. And then we have to have active perception so that the drone has autonomy during the flight so that the operator is not really overloaded, and in emergency cases. And of course, as I've told you, we have to define cinematographic rules and how we follow them during the mission, and we have to handle, of course, emergencies as well as events. For example, if a cyclist falls and this is a major event, how we detect it automatically and how we replan things. Now, regarding impact, if you go to this call expected impact, then you see the word measure being mentioned there many times. And this is our approach. First of all, we have a new domain, a new application area, which is AV shooting, and we have to provide service, and we have to measure the level of service. For example, can we get a new experience? How are we going to quantify it, if it's good or not? What's the quality of the videos that we're going to get? So we have to measure the service level for audiovisual shooting. And then we have to have measures regarding autonomy. These sports events last hour or hours. Drones are flying nowadays for a quarter of an hour, 20 minutes, depending on the battery you're going to use. So how we can really operationally extend the autonomy of multiple drones flying at the same time. And of course, since we have multiple drones and operators, then the question is how we can define new metrics to characterize the performance of the system. For example, how can we quantify the workload of the operator or of the director and try to minimize it? And then, of course, we have now new frontiers for TV program production. And there might be a revolution in this area because now you have a number of flying cameras. That's essentially what drones are. So the drone cinematography is going to produce something new or not? And as we already have seen, we have severe problems with flight barriers, obstacles due to regulations, concerns regarding privacy, public acceptance, and so on. So we're going to study all these issues and hopefully contribute to the standardization bodies. Thank you.
Good, thank you. Construction.
Yes. Good afternoon. My name is Julian Astudillo. I'm the coordinator of the FAESTUS project, and I belong to Tecnalia. The ambition of the project is to introduce new robotics and autonomous systems in the construction sector, which at this moment is the presence of the robotics is not very usual or almost non-existent. What we want to do with this project is to improve the way that one part of the elements of the building, the facades, are installed on the building, and also we want to improve the activities related to maintenance and cleaning. So what we want to propose is new automatized way to improve all the activities related to the construction and the installation of the facades. To do this, we based our research mainly on the cable-driven robots, You can see here an image of a big skyscraper with the robots across all the entire facade. With these robots, we can reach very high dimensions, and we can put all the elements of the facade in an automatized way. So the robot is going to make all the process related to the installation of these facades, the scanning of the building, the drilling of the different elements to install the anchorages, the installation of the modules of the facade. After the installation, we can remove and change some modules if we face some problems. And after the end of the construction, we can improve the maintenance and the cleanings of the facades. And we are going to focus on one type of facades, which is related to the curtain wall. So these big glass facades that we can find in the different buildings. Also, in the robot, we are going to have many different sensors, which are going to provide us all the information related to the position of the robot, the position of the curtain wall, and the different elements that we have in the facade. The main ambition or the main impact of the project is to avoid this type of things that we see in the picture. So we can see here some workers cleaning the facade. So you can see the size of the building, the risk that they face to clean or to maintain as the facade. So our main aim is to try to avoid this type of problems. So we want to introduce this type of elements in the construction sector in order to improve the quality and to avoid this type of risks and the many deaths that we have during the year related to this type of works. What we think is that we can reduce a lot the number of accidents related to the installation and the cleaning process to avoid this type of working. And also we can reduce the time of installation, and we can reduce the installation cost of this type of elements. And we choose one market in construction, which is a big market. We are talking about 30,000 million in the last year in Europe. And what we think is also that the solutions and the research that we perform in this project could be easily adapted to other fields of the construction sector.
Thank you.
Thank you.
The next type of project we have is on logistics and transport. So we have two of them first. So the core for robots and then the dreams for cars.
So hello, my name is Dimos Dimarogonas. I'm at KTH Center for Autonomous Systems. I'm the coordinator for this project. And the theme, as mentioned here, is coordination of heterogeneous robotic systems. And by heterogeneous, I come forward and say that we mean mobile robots or static robots, manipulation or non-manipulation endowed, and in the presence of humans that may want or may not want to coordinate with them. So here we have two examples based on the stakeholder companies also of our project. The one on the left involves human-robot interaction for manipulation. The second one involves robots in the presence of humans in office, for example, environments. For example, the robot on the right, which is a boss robot, may want to coordinate with a human in service robotics operations in the office, or it might want to just do its task while avoiding to collide with a human. So, yep. So, yes, sorry. So these two scenarios are examples of building boxes as scenarios between the cooperating robots we envision here. And in particular, we start with 4 case studies that involve coordination between different types of agents. And here, with agent, I also mean the human aspect. So in the first case study, we have collaboration between a human and a mobile manipulator. At the second one, we have coordination and collaboration between mobile and static manipulators, in this particular case. But then we go to mobile platforms that are not necessarily manipulation endowed, and we have two separate case studies, one in the case that the mobile platform wants to coordinate with a static manipulator, and one in the case that we have a mobile platform that wants to coordinate with a human. So these are building boxes for an overall scenario on the centralized planning that we envision. And in order to cope with this, we have 4 levels of different modules that we want to induce in the system. At the first level, we consider the planning layer, the coordination layer, and here we want to induce complex mission specifications to the team. And here we are going to use formal methods from computer science in order to induce such specification. At the second layer, we consider the actuation, the actual low-level control capabilities or not of the actual systems. And for this, 4 different case studies, we will consider the design of coordinated controllers thereof that sequentially implement the high-level plans. At the third layer, of course, we need to consider perception capabilities of the robots. And here we have two important features to consider: robustness and collaboration. So we want to induce robustness in the system, and at the same time, we want to exploit collaboration between the different robots, and we also need to take into account the potential dynamics in the environment. Apart from conceptual, that is a more theoretical integration, we also have a partner designated for the software integration of the modules. So when it comes to the impact, before going to the impact, I would like to say what is the high level, and here I see the bottom figure is induced by the text, but I would like to say that at the high level, we want to build on these 4 building block scenarios towards more complex tasks that involve more robots and bigger environments. For example, we want to consider robot failures in an environment with multiple robots and multiple humans or users in these robots. We consider new task arrivals, and we might consider changes in the environment. For example, this door in the middle might or not be closed. And here we want to induce plan adaptation techniques, and we would like to consider metrics in all the 3 different aspects involving planning, control, and perception in order to do adaptation of original plans in a way that is as close as possible to the original. But going to the 2 bullets on impact, we want to consider 2 points. First of all, we want to consider optimal or suboptimal if possible use of resources. We want to achieve faster accomplishment of tasks through decentralization, and this should be taken into account in the replanning. And a contribution that we also mentioned in the proposal is that of flexibility. We want more flexible multi-robot systems. This has a direct feature in the service robotics scenario we consider here on logistics, on service robotics transport. But at the same time, we want to go one step further in the impact towards manufacturing applications, manufacturing logistics application. So, thank you.
Thank you. I might remind you a little bit of one thing we've seen before, and imagine in a complete different sector, so dream for car.
Hi, so I'm Serge Till from the University of Chevre. I'm here representing Mauro D'Alio, who is the coordinator of this project and who couldn't be here today. So Dreams for Cars is about autonomous driving. And the thing with autonomous driving is if you want to build an autonomous vehicle, then you might want to collect lots and lots of data, and based on that data, somehow design a controller that will be able to drive around nicely and well. And the thing is, once you've done that a few times, that you have a robot that works, or a car that works reasonably well, then most of the time the situations are going to be absolutely fine. Even if you drive as a human, most of the time the driving goes absolutely swimmingly. There is no problem. What matters is really the rare events where things don't go all right and where you need to find out one way or another how to deal with a potentially critical situation that you didn't foresee. So, and if you're an autonomous vehicle, it's your designer that didn't foresee that situation, and how you're going to deal with it. And since you collect lots and lots of data, but most of the time all the driving is absolutely fine, you're collecting data about situations that you know how to handle, so they're not really that informative about how you're going to deal with situations that you don't know how to handle. So the question is, how do we get more data on rare events such as near misses, accidents, and so on, without actually crashing our autonomous vehicles all the time? And so the ambition of Dreams for Cars is to build a mechanism that we sort of call dreamlike mechanisms, where robots can use the actual data from real drives, so whether they were near misses or not, to build a simulated world where they can explore on lots of variations of these scenarios, build hypothetical scenarios, a little bit like when we dream, right? We recombine in sensory motor experiences we had during our wake states to create hypothetical scenarios that may tell us how to deal with unforeseen circumstances. And in this case, that situation, that architecture will then, these improvements from a dreamlike states will be transferred back to the real vehicle to hopefully make it improve its performance in real situations. The approach is therefore very cognitively inspired. So we look at how humans do this a lot, and we know a lot about that, so I'm not going to go into detail about it. But when we dream, we reuse our own sensory motor areas in the brain, and we use the same mechanisms. We just don't actually carry out the actions. We don't actually get sensory input. We simulate the sensory input. And this was done already in a previous FP7 project called Adaptive, where perception action system architecture was built in a real vehicle to make it drive. What we do now is add the ability to use the same architecture to create hypothetical scenarios and novel combinations in order to improve the performance in unknown situations. So, yeah, the impact really is basically everything you would expect if we're talking about autonomous vehicles. They have huge impacts in society and for the transportation sector and so on. But the two things I want to highlight is that because this uses a controller that's already been used in a previous project, it allows us to directly measure the added benefit of adding these dreamlike mechanisms to the same controller. And the other thing is that if you've been around in robotics for a while, then you've heard about simulation mechanisms used in robotics for a while in FP6, FP7. It's just back then it was a Capra in a box, and now we're talking about a real autonomous vehicle on a real world. So it shows you that the more basic research can find good applications in a societally relevant domain. That's it. Thank you.
So yeah, hello, my name is Achim Lilienthal, and I'm at Örebro University and coordinating this project. The name is ILIAD. It's about intralogistics with integrated automatic deployment, and what we are talking here about is safe and scalable fleets of forklifts, autonomous forklifts, AGVs, that operate in spaces that are shared with humans. So what we see here is an image of a warehouse and a traditional logistic system comprising, containing some automated vehicles, AGVs, some maybe human-driven, some human workers, and some other people who happen to be in this area, for example, here an operator. And there are also boxes of the contributions of ILIAD, and I will explain them in a minute. Now, these intralogistic services, they face a number of challenges. So there are market needs, ever more quickly changing market needs. There are short product life cycles and unforeseeable trends. And one way is that you actually build these automated warehouses, but that's a huge investment, and that doesn't work for all the scenarios. So whenever you have to have humans around, when you deal with bulky goods or when you deal with fresh food especially, these are our end users, they are in the food distribution sector, then that doesn't work. So what we are aiming at is to provide solutions for this intermediate step, solutions for flexible intralogistics that integrate with existing warehouses and that facilitate this transition to automation in those spaces shared with humans. Now we go back to this picture, and I'd like to explain a few aspects about the ILIAD approach. So first of all, we see here that the vehicles, they should learn from their observation about motion patterns in the environment so that they are able to predict that, for example, at this place, at a certain time, there is a tendency that traffic jams occur. And that will be then taken into account in the planning. What we also have here is the deployment is actually a huge cost factor and the barrier in the introduction of those systems. So we'll work on easier deployment, and especially by providing semantic mapping, the system will automatically identify common structures in the environment in order to ease the burden on labeling the places for the operators. Third, Everything here is integrated into a fleet management system that handles in an integrated way task scheduling, task assignment, coordination, and motion planning. And it handles contingencies in an online approach. So if one of the vehicles gets stuck, the system reacts directly to it. Next, we have flexible manipulation. So we will develop manipulators that actually handle to unwrap, this is quite tricky actually, to unwrap pallets and to move out the goods to another pallet, to commission. Finally, and that's very important, we have a fundamental treatment of safety. So we're in an environment shared with humans. So we work on human detection and tracking to make this more robust, but we also have a systematic study of safety. So we will build an injury database. So we'll study what happens to humans when there is a collision, and this database will be taken into account at all stages of motion planning and control. And for legible motion planning, so that we get predictable motion, we will work on communication of robot intent to the human and recognition of the intent of humans by the robot. With this, ILIAD will make an impact, of course, in the intralogistics domain, where we directly are working. This is rapidly expanding and craving for flexible automated solutions. ILIAD will especially allow smaller companies to facilitate and to gradually move towards automation of their warehouses. But we will also make an impact beyond intralogistics, especially by increasing the reliability and safety in multi-robot systems in dynamic environments. And then we will extend the state-of-the-art in a number of areas: reliability-aware mapping, just to name a few here, localization, integrated motion planning and coordination, manipulation, human-robot interaction, and so on. And finally, last but not least, the systematic treatment of safety will also provide a foundation for future safety standards. So that's ILIAD.
Thank you. Thanks a lot.
Okay, so my name is Erwin Prassler. Well, I'd like to present this robot project, and it's not a typo. It's robots rather than robots, but as you can guess, it has to do with robots also. So, but before I tell you a bit more about robots and robotic pods, here we go. Let me give you a few figures which motivate our work. The first figure is 25.3 million days per year. That's the time that is spent in European hospitals per year for doing nothing but collecting dirty food trays. So that's a lot of time. And if you turn this into positions, it's about 15,500 positions. Now you can say there's nothing bad about creating 15,500 positions. It's taxpayers, it's permanent jobs. But that's not correct. Actually, this extra time has to be spent by high-qualified nurses in addition to their regular business, okay? So the next two pairs of figures, which is of interest to us, and maybe of interest to you also, is 2 million euro per 10 years. So what is that? We have a partner in the consortium, and they actually asked a big hospital logistics HAV manufacturer for a quotation to automate their hospital. The hospital has about 500 sick beds. And they got a quotation for 2 million, so that was about 10 HAVs, just for the task to basically distribute goods coming in into from the receiving department into the wards. And they calculated and figured that it would take them about 10 years to amortize that investment. So that's a big barrier. Now the last figure is 24 different trolleys which are basically used in the hospital that cooperates with us for transporting whatever kind of goods, dirty linen, food, beverages, just name it. And also, in this hospital, they have about half a dozen different sick beds. Now, their expectation is that we come up with a solution that sort of reduces this barrier of a huge investment and at the same time deals with the constraints which they have. And what they say is the potential is enormous. So this is basically our starting point, and you can easily imagine that offering them an HEV for every specific vehicle, trolley, or hospital bed at a cost of 50,000 euro, which is basically the average cost of an HEV today, is a no-go. So, okay, before I tell you a little bit more about robotic pods, what is the impact, the expected impact? Well, actually, from the kickoff meeting on, and even before that, they told us that they have severe expectations, and they don't have a lot of humor. They expect that they have identified already a number of tasks which we're supposed to automate to relieve the burden on their nursing personnel, and they're waiting for that. So the impact, the expected result is a working system 24/7. Now, how much time do I have left?
About 1 minute.
1 minute, okay. What are robotic pods? Some of you may know that in maritime engineering, the big vessels, they have small engines underneath their hulls, which are rather flexible. They can be turned around their yaw axis, and they are self-contained engines, and with them you can basically maneuver a huge vessel in any direction. That's our idea. We are currently developing what we call a smart wheel. This is nothing but a robotic pod. It's something that you can place underneath a load. And the current design, the current specification is that one of these smart wheels, which is nothing but a small, compact, differentially driven pair of wheels, can carry 200 kilograms. So one pair of wheels can carry 200 kilograms, has a velocity of 5 meters per second, and has a traction of 200 Newton. So you need about 5 of these wheels to carry a load of 1 ton. And the idea is actually to configure these smart wheels to smart vehicles. And when we talk about smart vehicles, it's not one monolithic vehicle. It's basically the idea to have a large load like this podium and put these pods underneath it and then transport the whole thing.
Good.
Okay, I'm done.
The last project on logistics is refills, and it's about filling, in the supermarket, filling the shelves. Yes. So the floor is yours.
Good afternoon, ladies and gentlemen, and thanks, Cecile, for this opportunity. I'm Agostino De Santis from Consorzio Create Naples, which is the coordinating institution of refills. The coordinator is Professor Siciliano, who unfortunately didn't make to be here today. The acronym refills stands for Robotics Enabling Fully Integrated Logistics Lines for Supermarkets. And therefore, our main ambition is to completely revolutionize the current structure of logistics processes in retail stores thanks to robots. We think that retail stores are surviving to e-commerce because they offer the sensory experience of touching goods and the unique feature of human advice. At the same time, they have to stay competitive, and one can see that 60% of operational costs in a store are related to logistics. So we want to use robots to change the structure of this logistics. And this is an ambitious goal because it also requires robots which are over the current state of the art. The work of a supermarket clerk is tough, but also a robot clerk needs scientific and technological progress. And so our consortium is composed of 3 research groups: Consorzio Create, University of Campania, Italy, University of Bremen, Germany, and 2 manufacturers, KUKA from Germany and Intel, Israel, then Swisslog as a system integrator, and finally, the biggest German retailer in its branch, which is DM Drogeriemarkt. Our approach aims at changing the structure of the current fully manual logistic processes, where there are clerks monitoring shelves, delivering goods directly to the ground, initially filling the shelves, and then going back and forth from the back room where goods which are being brought to the ground do not fit on the shelves. In our smart refilling approach, there will be a number of robotic modules based on existing modules but redesigned, which will be able to monitor the store, pre-sort the items doing a depalletizing operation when the pallets are taken to the shop, then transport those goods toward the shelves, and then giving the possibilities of two scenarios. One where there will be a collaboration with the clerk, so the robot will keep the boxes in order to avoid the non-ergonomic posture of the clerk in order to reduce the effort for lifting. Or in the more advanced case, we also aim at a fully autonomous shelf refilling. This is based on previous expertise on semantic mapping, knowledge bases for manipulation, and sensors, and of course, reactive control. In the future, we think that this kind of technology may impact not only industry. Of course, it is self-evident that the retail stores will be impacted by this kind of innovation, and also the European Union manufacturers of robots may keep their market share in professional service robotics. But also the general public may benefit of still having a competitive supermarket and not be forced to buy from online stores. Of course, this kind of innovation also poses a number of issues related to ethics and legal and societal and economic issues, and we will have a dedicated work package on this in the project, since it is true that we will offer this way more attractive jobs in the retail environment, but at the same time, some jobs will be cut. Also the European regulation about load lifting are expected to change if there will be a robot helping the clerk. Of course, we also expect scientific advances in the research fields of our groups. Thank you.
Thanks a lot. So now we are done with the standard type of research and innovation project. And now we will go to two projects which I put under the community service and coordination. So those projects are supposed to offer services to the whole robotics community, and so they will need also your commitment and your involvement in their project. So we expect a lot of interaction between you and themselves, so it's the opportunity for the coordinator to present which service they can offer to you and how you can also contribute and benefit to those ones. So the first one is Rob Moses. Yes. Welcome.
Thank you. So I'm Sarah Tucci, coordinating this project, Rob Moses project. This is innovation action, sorry for the voice. Innovation action and system development technology, particular. So the ambition of Rob Moses is actually to realize a step change towards an industrial-grade software development software ecosystem, which is quite difficult to understand, but at the end it's about development technology. So the technology is there to build better robotic software. And this technology should be grounded on advanced software engineering methods and techniques. We will see something later about that. Our idea is that this ecosystem should be actually as open as possible. It means that the development technology should be accessible for the public, sustainable. It means that even after the end of the project, this ecosystem should live. And actually, the project lasts for 4 years, so we have time to work on that. And of course, what is really important is industrial quality of these development technologies that should actually be used to build better software. Rob Moses actually can be seen as a concretization of a digital industrial platform for robotics, which is actually a concept from the European Commission, and we are very proud to be partner on that. How to realize that? Actually, the approach is based on model-driven engineering, is a key enabler. So the idea is to resort to these techniques, to this approach, to bring in the robotics community. Model-driven engineering demonstrates to be successful in other industrial domains, such as, for instance, automotive, particularly good for intensive software systems, system integration, and I would say also compliance with high quality standards, for instance, safety standards. So this is really important. From a more technical point of view, I can say that actually we can promote composability and compositionality of a first-class citizen, which is not code. It's a more abstract representation of code, it's software models. The idea is that actually software models can help us to validate system-level properties of the system. This is particularly important in system integration, and as well to be independent of code-centric robotics platforms that are already out there, and preserving modularity as well. So concretely expected results for this project are, would say, delivering, maintaining, and disseminating a repository of software models and the tools that can validate the models, the composition of the models themselves, and the code that can be generated from them. So the tooling for content by construction, and of course, we want to have this open source software track. As I said before, this is important to us to have openness in the approach. How to realize that is not only about techniques, we also know that there are already a lot of tools and development technology based on this model-driven approach that already are there. The most important part is the community involvement, so the feedback we can gather from you. And for this, we actually plan a workshop series, and the first workshop will be actually here today after the coffee break at room O'Kill 2 and 3, so we can exchange about the project itself and also to set first priorities about what you need in terms of support for building bad software and robotics. And of course, the idea is to use the open call mechanism, so we actually have half of the budget, so 4 million for the open call, so for the community. That's important, I would say. So the impact, of course, the impact is quite obvious in some sense, is the professionalization of software development robotics, so improvement of the quality of the software itself and at reduced cost. This is quite obvious, but the original part I would say it's more in the commoditization of the basic robotics software, the software models and advanced modeling tools that actually will be the delivery of this project. And this enabled the growth potential market of new generative robotic systems that, of course, we already seen in the last presentation, and we think that most of them should be certification ready, and this kind of approaches can help on that. Thank you.
The next one is also in the same vein as community service. Next, this is yours.
Thank you very much, Cecile. I'm Carlos Hernandez from TU Delft, and I will present the ROSIN project. It's also an innovation action as a Robotics, and it's on ROS Industrial Quality Assured robot software components. So our ambition is basically to break the impasse we have in software for robotics. As we can see in this graph, robotics is not yet getting into different domains in industry from those traditional, mainly automotive and others. And we have been seeing in the last decades a lot of research and advancement that are not making it to industry. So the background for the project is to basically speed up the industrial uptake of the new advanced robotic application. And concretely, the ROSIN project will make the ROS Industrial the new open source industrial standard for intelligent industrial robots, and putting Europe in the lead. Probably all of you know about ROS and have heard of ROS Industrial. And we aim to make that the EU digital industrial platform for robotics. ROS Industrial is already there. It has a community, but has some shortcomings to make it to the widespread industry. These shortcomings are software quality issues because most of the components being developed by researchers, they are not yet qualified for industrial use. There is not yet enough widespread use of this technology in other needs apart from service robots, and it's also not familiar to many people in industry. So we will try to improve on these three shortcomings by addressing the software quality issue, promoting more relevant commercial cases, and making it more accessible to the community and especially to industry. For that, our approach is basically to overcome the two barriers we have identified. The first one, there is not yet enough components with a sufficient quality to be used in industry. For that, we have one specific pillar or line of action, which are the quality assurance tools, and we will be basically working on enhancing the already extant practices in ROS Industrial, which is continuous integration, unit testing, and code reviews, with new tools, with, for example, model-in-the-loop testing, model-based and model-generated testing, automated test generation, and novel methods for code scanning. And our main goal is to basically work with the already extant community of developers to promote quality assurance practices. The second barrier, which is the prisoner's dilemma, in which many companies see it interesting to use ROS Industrial or ROS components because of the capabilities they can extend their robots with, but yet they are not willing to take the risk to use it because they don't see enough other players using it. So we plan to break this risk barrier by using the cascade funding from the EU to finance new developments in ROS Industrial. We have more than 3 million euros available for focused technical projects, which are very focused projects to develop one feature, a new component, a new driver, maybe a software-related process, code audits, models, for example. As in Robotics, we are really happy to hear that there are another project. And so we have this funding available, and an education action line in which we will promote education in the industry. So our expected impact is basically to make ROS Industrial the new standard for intelligent robots and have systems like this one, in which we created in the past, well, still finishing Factory in a Day project. It's a system that won the Amazon Picking Challenge, but is yet not in the market because the software it was built for is yet not ready for certification. So we plan to make ROS Industrial a qualified platform for industry and have these applications out there.
Good, thank you. And now the last but not least, so now we have, for the first time, a project focusing on the end users, so the citizens and the society. What are their concerns? So how can we better understand their needs and concerns? So the floor is yours. Welcome.
Thank you. Is that too short?
On the right-hand side, you...
Oh, sorry. Hello, I'm Stine Trandemøller. I'm representing the REALer project and also the coordinator, Katrine Hasse, who is currently representing REALer next door in the ELS workshop. So, as Cecile mentioned, our main focus is on what we would call the end users, direct and indirect end users. In our project, we tend to call them the citizens. So the motivation behind this project is resting on a hypothesis that the distance between them, we see a distance between roboticists or the robot community, citizens, end users, and policymakers. And that causes little collaborative learning between these three groups, conflicting systems of values, so what do we expect to get out of the robots, why are they here, and some unintended impacts. So we don't see a full potential in the use of robots. There are some early signs of robot sabotage. People in the industries not cooperating with the robots. Skewed labor market might be an unintended impact, but also an altered human condition. So how does the introduction of robot in a workplace, for instance, change us as human beings, how we work? That's what we mean by that. So the main ambition of RELA is to then align these three groups, align the roboticist vision of a future with robots with what we call empirically based knowledge of the human needs and societal concerns. And on top of that, we wish to develop a proximity-based human-machine ethics that consider how individuals and community connect with robot technologies. And when we talk about proximity, it's a bit wider than the physical distance and nearness and safety. It's also how you perceive and interact and how robots, for instance, let me give you an example of a health robot introduced in rehabilitation of patients. So that contribution into that setting, how will that affect the physiotherapists? How will it affect their professional identity, for instance? That's part of the proximity understanding in the RELA project. So that would be the indirect end users. And we also hope to be able to increase collaboration and unleash a learning potential that we feel is not yet exploited. Our approach is very different from yours. It's not technology-led. We will study through ethnographic fieldwork, so we will go out and do observations, interview you guys, hopefully, in labs, but also stakeholders and affected environment to explore the different value systems that may be there. There obviously are some overlapping, but also some conflicting. Then we work with what we call a case-based sociodrama. Case would be a robot study that take in both from lab, but also from the affected environment. And we have what we call robot expert panels. We actually have one in June in Copenhagen. So if any one of you guys would like to join it, please come to me in the poster session. So we run these social dramas with the expert panel to bring in new perspectives in the robot community. So a different way of looking at your own practice. And in order to give the citizens a voice, a more democratic voice, we run these, plan to run these mini-publics where we take up another case, or maybe also the same from the robot expert panel, and discuss that with policymakers and citizens, expected direct and indirect users. So hopefully our impact will be the main project, the outcome of the project will be a RELA roadmap, which will be paired with an interactive toolbox, so which can help you sort of to give you guidance on new way of design processes, for instance, to help you improve them by bringing in the human factor at an earlier stage, is what we envisage at this point. Hopefully that will help create or increase, the collaborative learning between the different groups and communities. But also within academia, we are social scientists, and from humanities, we expect to be able to learn and collaborate with you and the vice versa, as Cecile mentioned. Hopefully that will be something our roadmap will give guidance to. And I hope it's not too provocative in this setting, but simply make robots more relevant for humans and society than we think is the case today. Good. So thank you very much.
Thank you. Thanks a lot to all the speakers and participants to the session. I hope you enjoy it as much as I did. So now what follows is that there will be the poster session downstairs. So please go and visit them and ask questions to the coordinator. And I will ask again here, it's an opportunity to ask all of the coordinators to keep really a high level of visibility of this funding. It's so important for the program that you display, you really explain also to the citizens what Europe is doing as well in this field and how we try to keep the lead and progress to make the society and the economy benefiting from this effort and this program. So please collaborate, exchange, and let's build together something great in Europe for robotics. Thank you again.